Okay, so we talked about combinatorial explosion. Hopefully, I've illustrated that to you pretty convincingly, that of the idea of combinatorial explosion. Uh, and so, because of this big problem, uh, Newell and Simon needed to figure out a way to come up with a more efficient way of searching through this space. And so we'll talk about that. But first, I need to talk about a few types of problem-solving techniques. And so one is called an algorithm, which we've talked about before. An algorithm is a problem-solving technique that is guaranteed to find the correct solution or show that no problem, or sorry, or show that no solution exists. Um, right. And so we've talked about algorithms as like a series of steps. And this is not inconsistent with the definition here. But in the problem solving context, it's sort of it's a technique or a series of steps that are guaranteed to get to the correct solution, right? So, like adding 25 plus 50, there's an algorithm that you can use, right? You line them up, then you add the ones, and then you carry whatever's left over, then you add the tens, and that gives you the answer, right? That's an algorithm. And an algorithmic search is good if the computational complexity of the problem is small. However, you probably wouldn't use an algorithm in a game of chess because of your limited resources. And so, yeah, as I've implied, an algorithm guarantees a solution, right? Or at least guarantees a solution when one exists. But the problem is, so that's a good thing, guarantees a solution. The problem is that it can be time consuming, right? Um, and so, in contrast, another kind of technique is a heuristic. So, a heuristic is a problem-solving technique or a set of rules that aren't guaranteed to find a solution, but they work reasonably well. And so, yeah, heuristics are like strategies that are supposed to make it more likely that you'll get to the correct answer, but not necessarily. Okay. And again, these are like, you can think of these as like rules of thumb or mental shortcuts. So, like in the game of chess, rather than using an algorithm, you may use a heuristic strategy. One strategy that you could use is trying to control the center of the board, or so I've been told. Of course, this won't guarantee a solution, but it will be a pretty good strategy. And as I mentioned, right, I think I did, kind of. So it is the benefit of heuristics is that they are computationally easier and less time consuming as a result. The problem with them is that this solution is not guaranteed. And so, human intelligence aside, Newell and Simon were aware of this issue of combinatorial explosion, and just for the purposes of building a general problem solver, Newell and Simon developed a heuristic that computers could use when the search space is too large. Now, this is called a means end analysis, which we're going to talk about a little bit, uh, but we're not going to talk about it now. We're going to talk about it later. I just wanted to mention that. So let's talk about heuristics. One heuristic search is called the simple search. And this, as you mentioned, is very simple, right? So you start at an initial state and you just continuously move toward the goal state. And is also called hill climbing or a greedy search. So the core idea is just you're always moving to the state that seems closest to the goal. Okay. So let's see. I'm going to illustrate this with the traveling salesman problem. All right. So here it is again. Notice how they're different numbers. I just did that because this is more conducive to showing why the simple search can fail. Right. So same idea though. You start at A, right? And you evaluate all the distances from A to B, A to C, A to D, A to E. Well, let's see. A to B is 20. That's pretty short. A to C, that's 50. A to D, that's 120. A to E, that's 60. So you would pick B, right? Because that's the shortest distance and it gets you closest to the goal state, right? The optimal solution is the idea. And so you choose that. Okay, great. And then now that you're at B, right? Well, you're at B. Well, the shortest distance is going to be B to C. Okay, you can check for yourself, but it is. And then when you get to C, now the question is, do you go to D or E? Well, D, if you're at C, D is 85, whereas E is 80. I know it doesn't quite look like it, but uh, so you would go to E, right? And then you go to the last remaining city, which is D, and then go back to A, right? So this gives you this trajectory gives you a cumulative total of 290 miles. Okay. Well, problem with this is that's not the optimal solution, right? Uh, the optimal solution is both of the optimal solutions, there's actually two of them, they lead to a cumulative distance of 220 miles. So the reason why this was a why the simple search sort of failed is because it was misled by the short distances between A and B, as well as the short distance between B and C. So in our example, traveling from A to B was the shortest distance. Uh, and so that is the city that would be picked, right? However, this is a greedy choice in a sense because although it cost the least, so to speak, right, it ended up costing us more in the long run. Okay. Yeah, so it doesn't take into account this simple search or greedy search. It doesn't take into account the big picture. It doesn't look at how is this choice going to affect the cumulative total, right? It only looks at the sort of immediate steps, right, that it can take, but it doesn't look at how those immediate steps are going to affect downstream steps, is what I would say. And so the problem that what the core of what this gets at is sometimes temporarily moving away from the goal state is the best move. And I'll show you what I mean, right? But we can think of this as like if you're climbing a hill, right? So as I said, it's also called a hill climbing strategy. So if you're climbing a hill and you get to a peak, right? You get to this like peak, which we can call a local maximum. But if you get to this local maximum, then going either way will actually take you farther away from that peak as well as the global. Well, I guess it takes you farther away from the local maximum, right? From that peak that you're on. So the problem though is that if there is a peak that is higher than the current peak, so a global maximum, it's the highest peak of the peaks, then this simple search would get stuck at that lower peak. And so this search doesn't really think about the big picture, which means that it can get stuck at a local maximum or a suboptimal solution. Okay. Um, and so yeah, I'll just foreshadow what I'll talk about with the means ends analysis, right? So suppose you're at the mountain separated by this sort of deep valley, right? So you're at the local maximum, and then there's a deep valley. Hill climbing would refuse to go downhill. But the means end analysis, which is another kind of search, as I mentioned, would recognize that going down first is necessary to cross the valley and to climb the true peak. Okay, we'll do one more. Okay, now this one's easy. This is the easiest one, I think. Working backwards is just simply rather than starting at the initial state and going to the goal state, start at the goal state and trace the path in reverse to reach the initial state, right? So if you have this is people do this all the time with like multiple choice math problems, right? Rather than trying to solve the problem, you just plug A into the problem and then B into the problem and C in the problem and then D in the problem to see if, which one's correct, right? If I plug in 5 for X, does it give me a Y equal to 10 as the problem says it would? If so, then it's correct. And so this is most useful when there are many different operators that can be applied to the initial state. So it's not clear how to go about uh, how to go about the problem when you're at the initial state. Then it's easier to maybe start at the goal state. And it's also most useful when the number of potential directions from the goal is small. So if you only have four options in a multiple choice uh, problem, for example, you can just start at each goal state, right? Whatever that, whatever each one you think is right, and then uh, go backward. Here's a cool talk. It's a very short talk on chess. I'm not going to play it, but you should watch it if you'd like. Um, yep. Okay. In the next video, we're going to talk about means end analysis and the missionaries and cannibal problem.